we learned from the previous section about real gases, and that real gases are more accurately described by the van der Waals equation, which takes the form P equal to nRT over V minus NB minus A times N squared over V squared. If you notice in this equation, there are two constants that are introduced, A and B. These two constants serves as a modifications to accurately describe real gases more. Now this constant A here, this describes the strength of the attractive force that exists between two particles in a gas. When two particles of gas are at a certain distance, okay, they tend to attract one another. Okay, now this happens even for neutral particles or uncharged particles, and we will see the reason why in the next succeeding slides. Now as the attractive force becomes stronger, this A here becomes bigger, the value becomes bigger. Alright, so that's the constant A. Now the constant B here, this describes the excluded volume of the particles or the molecules in the gas. Now excluded volume is defined as the volume occupied by 1 mole of the gas. So in this case, suppose we have two gas particles. Now gas particles, they occupy a certain volume. Okay, they're not always assumed to be point charges. They occupy the same volume. And when two particles are very near each other, okay, they tend to repel one another. And that's and that is because one space cannot be occupied by two particles at a time, so they tend to repel one another. And also these particles here, they contain electrons around them, and same charges tend to repel each other. So that is the purpose of this constant B. The bigger the value of B, the higher the repulsion that happens, between two particles. All right. So how does these two constants affect the pressure of real gases? Now A here, as A increases, what happens is that the pressure that we get, okay, that we predict using the real gas is smaller than the pressure we would have get if we use the ideal gas law, because this is a minus sign here. So as this becomes big, the pressure is smaller than the predicted ideal gas pressure. Now if B is increased, if the constant B increase, what happens is that this term here becomes bigger. Okay, now what happens is that the pressure, okay, used to predict real gases becomes bigger than that of the ideal gas. Okay, so this two opposing effect is incorporated in this van der Waals equation, this equation. Okay, and so this equation, whatever the pressure we get here, this more accurately describes real gases than using the ideal gas law that we learned earlier as well. Right? In this slide, we will learn about the origin of these two modifications. We will examine more in detail the origin of this A and B constants in van der Waals. Now we have here the Lennard Jones potential. The Lennard Jones potential takes the form V of Lj of R, meaning it's a function of the separation distance, is equal to the 4 epsilon times sigma over R raised to 12 minus sigma over r raised to 6. Okay. Now this equation here describes this curve. So it acts as a model, to create this curve for different particles that are interacting. Now sometimes this potential is called the 12-6 potential. Okay, in some other books they are called this. It is called this way. Okay. Now in the next slide we will see in detail, and we will examine in detail this curve. Okay, now here's the curve that we saw earlier. Okay. Now in this curve there are three important parts that we need to know. The first one is this part here. Okay, so if you notice this curve, Lennard Jones potential have this distinct shape. It's like there's a almost vertical line here, and there's a well going around here, a point of minimum, and an increasing line which approaches the zero line here. Okay, now the lowest point here, the minimum, okay, has a certain potential, okay, corresponding to this. Now at this point, the two particles are at a optimum distance. Okay, it is at a distance in which, okay, they're not interacting at all. Okay, they're not producing any force to each other. So the net force at this point is 0. There is no attraction, no repulsion. Okay, and at what distance this is? Arbitrarily, this example is at 1.12. Okay, since the x-axis is defined as r times sigma, okay, and this r represents 1.12, okay, then this distance here, the optimum distance, corresponds to 1.12. Right, so that's the distance. Now that's the first important part of the curve. The second important part of the curve is the one on its right, and this side here. Okay. Now this part of the curve represents the attraction that goes between the two particles. Now this happens if the separation is slightly farther away from 1.12. Okay, if you pull them out, okay, there exists an attraction at this point. Now the reason is that, okay, first, these particles are neutral. Okay, suppose they're neutral, okay, with a positive charge in the middle and the particle surrounded by electron cloud. All right. Now these two, when they near collision, they tend to attract each other, and that attraction causes the particles to become unsymmetrical. What it means is that the electrons tend to be on one side, okay, leaving the positive charge on the other side, and this happens for both particles. Okay, and this asymmetry causes them to have a induced dipole. And we learned earlier then that if there's a dipole going on, there's a certain attraction that can happen between these two dipoles. Though this is short-lived, it causes a measurable effect on gases. Okay, it causes a certain effect. Okay, and this is the origin of the attraction that goes on at this part of the curve. Right? Okay, now the third part of the curve is this part here. This curve here, which is almost vertical and going up. Okay, and now this represents the repulsion. Okay, we mentioned earlier that two particles can occupy the same space, and so they tend to repulse each other. Okay, so as you can notice here, a small change, okay, a small change in distance causes a huge increase in potential energy. Okay, and this almost vertical curve here represents that you cannot make them come together any more closer. That is because they're surrounded by their electron cloud. Okay? And then they tend to repel one another, as described by this huge increase in potential energy that is going on here. Okay? So this attraction part here is represented by this part of the equation with the Lennard Jones potential. Okay, so as you increase r, as r approaches infinity, what happens to the potential is that it approaches 0, as what you can see from this line. And this part here of the equation represents this part, the repulsion part of the curve. Okay? As r approaches, say, 0, of course it cannot approach 0, but near 0, as it approaches near 0, what happens is that the potential approaches infinity, as shown by this upward directed arrow. Right. So this is the Lennard Jones potential, and this describes the attraction and repulsion that goes on generally in most particles of gas and or liquids or solids. Okay. Now in the next slide, we will see how these things look like. Now this curve is this linear potential curve is created by keeping one particle fixed. For simplicity, they keep one particle fixed while one particle move, and it looks like this. At a slightly far distance, okay, they tend to attract each other, and when they meet each other, they repulse. So it goes like this, back and forth. Okay, and as this part here goes near, look the change in color. It represents the increase in sudden increase in potential energy that happens when the two become very near each other. So this is what's going on between the two particles if you look at them, if you could look at them in the microscopic level.